So I'll be talking about CoReCast, collision-resilient broadcasting in vehicular networks. This is work done at The Ohio State University in collaboration with Toyota. So messages in vehicular networks can contain information about car speed, car proximity, road safety conditions, like if there's an accident ahead or if there's black ice ahead. It's estimated that by using these messages, we can reduce the number of accidents by about 80%. And since there are about 5 million accidents every year in the United States, the importance of these messages cannot be overstated. So these messages are short, frequent, they require a low delay in transmission and high reliability in reception. So the vehicular network scenario has its own complexities and opportunities that we have to deal with. In terms of complexity, this is a decentralized broadcast scenario where everyone wants to send data to everyone else. Additionally, there are differing link qualities, so we can't just look at one link and try to optimize the throughput on that one link. Lastly, this is a dynamic environment, so we don't have enough time to, say, identify who transmits when or who coordinates all the transmissions. In terms of opportunity, compared to, say, cell phones or sensor networks, we have a lot more power to play with, so we can get a little innovative with that. Also, oftentimes we'll have access to a GPS signal, so we should be able to leverage that also in some way. So given the requirements of these packets, their short size, their frequent transmission, and the opportunities we have a few goals or some highlights for CoReCast. We would like multiple cars to be able to transmit simultaneously and share the channel capacity. Since these messages are small, it should be possible for them to be transmitted concurrently and decoded concurrently. Since we have a GPS signal, we should be able to synchronize these transmissions or transmit them in a slotted way. And since we are not really power limited like sensor networks, we should be able to transmit multiple times in order to increase the probability of successful reception at the receiver. Additionally, since we are doing concurrent transmissions, we would like the receiver to be able to decode messages from colliding signals. And lastly, we would like these cars to work in a full duplex mode so that they don't have to wait for a reception to complete before they can transmit. So this will speed things up a lot in terms of delay times. So in order to achieve this system, there are a few challenges, and I'm going to talk about two of them. The first one is channel estimation for multiple transmitters. Now, the receiver needs the channel between itself and a transmitter so that it can decode the data. But usually, channel estimation is done without any interference, and therefore having concurrent transmissions is going to make this difficult for us. Additionally, we don't have time to do channel estimation for each transmitter one at a time. Again, this is because of the dynamic nature of the environment. So let's look at typical channel estimation. What happens there? So say there's a transmitter that transmits a known sequence, a training sequence, or a preamble called PA. Then the received samples will be equal to the transmitted samples multiplied by whatever the channel between the transmitter and the receiver. Written in a matrix format, it looks like this, y equals xh. Now I'm going to keep referring to this quite often throughout the presentation, y equals xh. But in this case, we know what the received samples are, we know what the transmitted data was, so we can easily find out what the channel is. So what happens when there are two concurrent transmitters? Now, as long as the preambles that these transmitters use are uncorrelated and almost unique to the transmitter, not much changes. So the number of columns in X increases to 2, corresponding to 2 transmitters, and the number of channels in the H vector also increases to 2, corresponding to the channel between the receiver and each of the transmitters. So this also seems solvable. So what exactly is the problem that we have? The problem we have is that in a dynamic vehicular network, the transmitters are not known all the time because a car can enter and leave over time. So that means that we can't really formulate the exact X matrix of the expected preambles in the signal. So X is unknown, which means Y equals XH is unsolvable. A naive solution to this would be to assign everyone globally unique preambles and then assume that the signal that I have received has all of these preambles and try to solve y equals xh. What will happen when you solve it is that the preambles that really are present in your received signal will have non-zero values in h. The problem with this approach is that it's really expensive. So if you consider a scenario with n cars and you use something like a Walsh code or a Gold code, which is typically used for preamble generation, the preamble length will also be order n, which means that x will be of size n cross n. And since n for globally unique preambles or globally unique cars, it will be in the order of millions or billions, this is extremely large in terms of space and time complexity. So our solution to this problem is sort of a divide and conquer approach where we solve smaller problems and then sort of build up to the complete problem. We separate preambles into hierarchical groups, and we're interested in identifying which are the active groups that are present in my received signal before we narrow in to the exact preambles that are present in my signal. Additionally, we use shorter preambles, which are of length log n. Now, people who know about this will say, oh, you now have an underdetermined system and you can't solve it using normal techniques. And so for that, we end up using a technique called compressive sensing, which comes with its own conditions, but we satisfy those, and so we're good over here. So the end result is that we can break down the problem of solving y equals xh into many smaller problems which have manageable x's. So this slide shows a toy example of how we sort of organize the preambles. So say we have 512 preambles. At the first level, we'll say group them into 8 groups, and these groups can be distinguished using the first few bits of the preamble. At the second level, each of these groups will be divided into 8 subgroups again, leading to 64 subgroups. Again, these 64 subgroups can again be uniquely identified using the next few bits of the preamble, so on and so forth, until at the last level we have uniquely identifiable preambles. So let's go through an example. Say you have received a signal and an oracle tells you that the preamble 111 and preamble 888 are actually being transmitted. But how does CoReCast go about identifying them from the collided signal? So first we use the first few samples of the received signal to formulate equations to identify which of the possible 8 groups are present in the signal. So right here we've reduced the search space for 512 to just 8. And using compressive sensing, we can identify the 2 groups that are active. By using this, we can again reduce the search space for the next stage, where we use the next few bits of the received signal. And we're only interested in identifying which of the 16 children or 16 subgroups are present, because we've disregarded all the others since we have this information from the previous level. Again, we can solve this using compressive sensing and identify that these 2 subgroups are present. And we can continue this process until at the very last stage, we have identified the unique preambles that are present, and at this point, we also know the channel of each of these preambles. So that was the first problem. The second problem that I want to talk about is controlling the number of transmitters. So I did say that we want concurrent transmissions, but we don't want everyone to transmit all the time. And the reason for that is because channel capacity is limited, and it gets divided by the number of transmitters. So if there are too many transmitters, neither one of them will get enough of a good link to the receiver to get any meaningful data across. So we would like to limit the number to say 10 or 20 or whatever the application desires. So in order to do this, we use the idea of coarse counting in the frequency domain. Just a sec. In the frequency domain, the idea here is that cars will transmit an OFDM symbol, and they'll put a 1 in one of the subcarriers. And different cars will put 1s in different subcarriers. They can choose the same subcarrier also. And what will happen at the receiver is that you will receive the combined power spectrum or the combined OFDM symbol. Now from, let me just get a pointer. Yeah, so now from this combined power spectrum, you can use some techniques to estimate the number of transmitters in your vicinity. So by using this estimate of the number of transmitters in your vicinity, you can compute a back-off probability. The back-off probability that we want to compute should be such that if people transmit with this back-off probability, at most m concurrent transmissions will happen. And now this back-off probability needs to be broadcast again so that everyone knows what back-off probability to use, and we use the same idea. But in this case, the subcarriers of the OFDM symbol correspond to a back-off probability. So if my back-off probability is 0.1, I'll just look up which subcarrier I should put a 1 into and then transmit that again. Again, it will go through this process where at the receive end, you will see a distribution of a power distribution, and you'll pick the most conservative back-off probability because you don't want to go overboard. So notice that for all of these steps, we don't need to do detection and we don't need the channel information. We don't need to do detection because we are time synchronized, so we know when this packet is supposed to arrive. And we don't need the channel because information is encoded in the power of the subcarrier, not the phase. So putting these 2 parts together, we define an epoch to contain 1 estimation phase and 1 data transmission phase. In the estimation phase, the cars identify how many cars are there in its neighborhood and compute a back-off probability. And then in the data transmission phase, they end up transmitting data multiple times, different packets. This is where the preamble detection, channel estimation, and decoding happens. So putting it into an example or something that we saw in the first few slides, say there are these 6 cars and they want to use CoReCast to exchange information. So in the first step, they'll do some estimation. They'll find out, okay, there are 6 of us, and I think the channel capacity can only support 3 of us. So they'll compute some backoff probability, and then using that backoff probability, they'll say, okay, in the next slot, some of us will transmit, some of us will back off. And the next slot, again, a new set of people will transmit, and someone else will back off, and so on, until the next estimation phase where they'll compute a new backoff probability. We do this because the environment may change, the number of cars may change, and so you need to re-estimate the backoff probability quite often. So I've only spoken about 2 of the problems that we had to solve. There's a lot more that I haven't spoken about, like how do we actually decode from colliding signals. This is a bit important, so I'll give you a bit of a heads up. We use techniques like successive interference cancellation and combining signals across multiple slots to decode these collided messages. There's also a lot that goes into constructing these preambles so that we can solve them nicely in this hierarchical fashion. But for that, I would refer you to the paper, or you can just shoot a question at me in the Q&A. So to evaluate the idea, we had a setup with just 3 cars. We drove on city and highway roads, and we had a basic full duplex setup where we were able to get about 70 dB of self-interference cancellation. We used USRP N210s and a GPS receiver to synchronize these USRPs in time and frequency. And this is the mess that was inside and outside our car. For a session that says, say no to wires, we use a lot of wires. So the objective over here was, a lot of people might say, hey, you only have 3 cars, it's not realistic. But we're just graduate students, we don't have an army of people driving around cars collecting channel information. So all we want to show is that the GPS synchronization, the self-interference cancellation, SIC combination, all of these let us at least do better than TDMA for this setup. So that is the first thing that we measure. We measure throughput. So how many slots does it take for a node to decode all of its neighbors' messages compared to TDMA? So we're only comparing gain over TDMA. And we compare the full duplex CoReCast approach to a half duplex approach, which is either CSMA or a probabilistic backoff. And we see that the half duplex approaches, on average, do only half as well as TDMA, whereas CoReCast, with all of its successive interference cancellation and smart coordination of these nodes, is able to do more than twice better than TDMA. The next thing we measure is, so Ohio doesn't have a lot of urban canyons, it's mostly flat, no really high buildings. But we wanted to see what happens if the GPS signal is lost. And in order to emulate that, what we did is, first we would attach the GPS antenna to the USRP and let it synchronize, or to the clock and let it synchronize. And then after that, we would remove the antenna for about half an hour and see how bad the synchronization gets over the course of half an hour. So we see that when the signal is attached and we have a good GPS signal, we're almost always within 1 sample of each other. So if 2 cars are transmitting, they almost transmit during the same nanosecond or picosecond. But when we remove the GPS antenna, even then about 75% of the time, the clocks are able to keep their synchronization with the GPS, since these are GPS synchronized clocks, disciplined oscillators. And in the worst case, the misalignment is 3 samples. But since our cyclic prefix is longer than 3 samples, this is fine with us. Next, we use the channels that we collected during our experiments to do some trace-based simulation using Sumo. We compare it with the DSRC protocol, which is 802.11p, a utility optimal version of CSMA, and an omniscient protocol, which basically knows the locations of all cars, knows all the collision domains, and schedules transmissions so that they don't collide. The first thing we measure is reliability. That is, what percentage of a node's neighbors get its message before the next message is due. And for a low message generation rate of just 10 messages per second, we see that the omniscient protocol and the CoReCast protocol are able to guarantee 100% reliability regardless of the size of the neighborhood. Whereas, almost expectedly, the CSMA-based protocols end up degrading in reliability as the number of nodes in the neighborhood increases. We then increase the message generation rate to 200 messages per second, And we see that all protocols deteriorate a lot, but still CoReCast is able to outperform even the omniscient scheduling protocol. The next thing we measure is delay, that is how long before all of a node's neighbors get its packet. And over here we see that there is an order of magnitude difference between the omniscient and CoReCast protocols and the CSMA-based protocols. Again, I feel this is somewhat intuitive. As the number of nodes in the neighborhood increases, the delay that CSMA-based protocols experience increases exponentially. And so when we zoom in to just the CoReCast and omniscient protocol results, we see that the CoReCast protocol still beats the omniscient protocol, regardless of the number of nodes in the neighborhood. So in conclusion, we've presented a collision-embracing MAC protocol which performs better than CSMA-like protocols or even the omniscient protocol for the vehicular network environment. We see that on average, we're able to get a 15x lower delay than the DSRC protocol and an 8x higher reliability when the packet generation rate is high, again compared to the DSRC protocol. And that's it. Thank you.